Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be deriving the Hawking effect from a bit of a different perspective. So let's begin. So in the last video on the Hawking effect, we derived it by looking at an observer that's hovering above a black hole. And we said that the observer above a black hole will describe their quantum field differently compared to the observer that's falling into a black hole. As a result, they will disagree with the number of particles in that region of space. We can also derive this in a different way. We can look at only one observer that's very far away from a black hole, and we can look at a sphere that collapses into a black hole. And essentially, the sphere will disturb the quantum fields around it, and which will look like to the far observer as particles in a way. So how do we actually make this a bit more rigorous? We are looking at a sphere, right? Here's a sphere that over time shrinks into a point mass, and that point mass is a black hole. Now we actually describe this in space-time like this. We are going to only consider one dimension. So a sphere in one dimension is going to look like a line segment. So here I have the sphere written right over here, and over time the sphere is collapsing into a point, and that point is a black hole. But at the Schwarzschild radius, which is this one right over here, the Schwarzschild radius, the event horizon forms. So what's in the red is the event horizon. And the event horizon like grows a bit, then it just like stays constant after some time. And that's how we kind of describe a gravitational collapse in a space-time diagram. Now, what happens if you consider a quantum field around this collapsing sphere? Well, say we have some light rays in the past. So here we have a couple of light rays. We're going to use light rays to kind of like be an analog to a quantum field. So we have a bunch of light rays just chilling in the path. They're just chilling, right? And then look, one hits the collapsing sphere, but it's no biggie. They pass the sphere just fine, and they leave the sphere just fine. Here we have this one. It hits the sphere. Oh no, but it's okay. It leaves the sphere just fine. But the third little piggy, it's going to go over here. It's going to hit the collapsing sphere, but oh no, it gets sucked into the horizon. Not really sucked, but and then it falls towards the singularity. That's a cool arch we got over there. And then so this one over here, similar fate. It's going to hit the event horizon. It's going to collapse to the singularity. So some of these light rays are going to escape the sphere, will enter the sphere, and they'll just leave it. But others are going to like hit the event horizon, right? And they're going to like go towards the singularity. But for those that actually leave the sphere, something strange is going to happen. They are going to experience a redshift as they leave that event horizon, or as they leave this collapsing sphere. And why is that? Well, it's true for all bodies with mass. If you leave some gravitational object, you're going to lose energy. Your kinetic energy will be converted into gravitational energy. Like if you were to chuck a rocket to space, it's going to lose some of that kinetic energy as it becomes that potential energy. So if you have a sphere, just a sphere that's not like moving at all, there's going to be a bit of a redshift as these light rays approach the sphere. Sorry, a bit of a blue shift as the light rays approach the sphere because of the opposite effect. Something falling down towards Earth, right? The potential energy gets converted to kinetic energy. But when the light rays leave the actual sphere, there's going to be a redshift. And essentially, if the sphere is static, the redshift and the blue shift will cancel out. So the field in the far future will have the same form as the field in the as the light rays in the far future will have the same form as the light rays in the far past. But if your sphere is collapsing to a point, what's going to happen is that these do not cancel out. You're going to have an overall redshift in the future, right? And that's what happens here. We have a collapsing sphere. These light rays in this outs region, we call this the outs region. Let's use a different color. Let's use nice indigo. So these light rays in the out region will have a different form compared to the light rays in the in region over here. And now we can actually extend the analogy to a quantum field. Just like how the light rays in the out region will be redshifted, and the quantum field in the out region will be shifted as well. And the quantum field in the out region will have a different form of a quantum field in the in region. Now, what do we get when we have two different quantum fields? We get difference creation and annihilation operators. And as a result, an observer in that far out region will see particles. So say like this quantum field over here, there's a vacuum, there's no particles. With this quantum field over here, A of k will act on the vacuum state and give us 0. Well, now the quantum field in the out region, right, because of this redshift, it's going to scatter, and the actual form will be different, right? You can clearly see that it's going to be different over here. And we're going to have, say, A tilde of k instead of A of k. So it can act on that same state that we previously said was a vacuum and give us not a vacuum. So the observer in the far out region is going to see particles coming from that black hole. Now, here we use light rays, right? We're using them to kind of give an analog of quantum fields. Of course, quantum fields, they don't travel through these nice lines, they're waves. But the same thing is going to apply here. If you kind of look at a wave that's approaching this black hole, it's going to be red shifted in the out region. So how do we actually show this mathematically? Well, here's how we do it. Oh, also ignore this thing over here. That's just a proper time. This is my third take of this video, actually. The first take, the mic was not turned on. The second take, the thing just didn't save. The video just didn't save for some reason. So if I seem tired or exhausted or out of breath, that's probably why. I spent a very long time on this video. So I apologize for that I apologize for that up front. But regardless, let's continue on with the video. So yeah, so that thing that was here, that was left from the previous takes, and I forgot to erase it. So just ignore that right over there. So how do we actually describe a quantum field that's clearly entering the sphere and leaving the sphere? Well, we solve the Klein-Gordon equation. So the standard form for a quantum field, right, in terms of T, R, theta, and phi, is this over here. And then, essentially, we do not want to look at the angular terms because they kind of suck. So we are going to ignore the angular term in this video. And from here, we can solve the radial equation to find the form of the radial part of the quantum field. If you guys do not know how we get from this step to this step over here, I recommend watching my video on the radial equation. I think that's the video where I derived this. We call this term over here, this is the centrifugal term. And this term is going to make solving this equation pretty hard. So what we can do is we can solve it by not solving it. We can consider the case where r approaches infinity or minus infinity. So this corresponds to us considering an observer or the field very far away from the black hole. And to be clear, the black hole is going to be centered at r equals 0. So we are going to pretty much shift this over here to here. So it's going to be centered at r equals 0. So if you look at r approaches infinity or minus infinity, what happens is that these terms go away because r is in the denominator, so they shrink to 0. This will give us 0, right? So as a result, we are left with this equation right over here. R plus omega squared, r equals 0. Omega here is the energy, by the way. We are considering a massless scalar field. So due to the equals mc squared, the energy is going to equal the momenta. So you might also see me write this as k, since E equals k in this case. All right, so now we can do some more stuff. We can rearrange this over here to give us minus omega squared r. This is r of, I should speak more slowly, I'm sorry. I'm just really tired right now. So r of r conjugate equals e to the I omega t, or sorry, I omega r conjugate, and then e to the minus I omega r conjugate. Those are the solutions, right? So we can take a combination of them to get a e to the I omega r conjugate plus b e to the minus I omega r conjugate. And then we have to look at the time factor, the wiggle factor right over here. We can plug that in, giving us phi of r conjugate t. That's going to be a e to the I omega r conjugate, e to the minus I omega t, plus b e to the minus I omega r conjugate, e to the minus I omega t. Doing some combining stuff here, gives us I omega r conjugate minus t, plus b e to the minus I omega r conjugate plus t. Now we define some new coordinates. Let's just call this over here. Let's call this minus u. Let's call this guy over here v. And as a result, we have phi of uv equals a e to the minus I omega u plus b e to the minus, or b e to the I omega v. And we actually derived this guy in the video on the Hawking effect. So if you guys don't understand this derivation, I derived it in a more focused setting, I guess you could say, in the last video on the Hawking effect. So we have this over here, right? We call this u and v. We call those the light cone coordinates, or the light cone tortoise coordinates. Now we're using a conjugate k and a of k instead of a and b here. So yeah, this is the formula for the quantum field in the Schwarzschild spacetime. And basically what we want to do now is we want to only look at the plane waves themselves, because it's going to be easier for us to just focus on the plane waves and see how they change, and then write out the Boglie-Walsh transformation to get out a of k and a conjugate k, if that makes sense. So basically, these parts are kind of irrelevant for what we want to do. So we can kind of pretend that phi of u and v is going to be e to the minus IKU plus e to the IKV. And then to be clear, u is just t minus r conjugate, and v is t plus r conjugate. I think in the video on the Hawking effect, we defined it as r conjugate minus t. It doesn't really matter how you define it, we get like the same thing in the end. There's a bit of a problem here. We derive the formula for the field for a Schwarzschild spacetime, right? And the metric for a Schwarzschild spacetime is just c of r du dv. C of r du dv. And here's the formula for the field in the Schwarzschild spacetime: e to the minus IKU plus e to the IKV. But we have a sphere, right? We have like a legit sphere here. The Schwarzschild spacetime solution, that is a vacuum solution, meaning that we don't have any matter anywhere in the space, right? So we can't pretend that we can't pretend that the space is completely empty, right? We have a field here that's chilling here with nothing inside the space. No, we have a sphere inside that space, right? We have a single sphere inside empty space, right? So basically, outside the sphere, we have a vacuum. So outside the sphere, we have that Schwarzschild solution. But inside of the sphere, guys, there's matter sitting right there. We can't pretend that we can't discriminate against this ball. We can't pretend that there's no matter there. So basically, this actual formula for the field is only going to be valid outside of that collapsing sphere. Inside the sphere, we have a different metric. So in order to describe the quantum field passing through the sphere, yada 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 yada, we have to look at a different metric inside that sphere. So how does that work? Well, first of all, we said that u was t minus r conjugate, and v was t plus r conjugate. Well, think about it. If we have a sphere here with the radius r. So here's the sphere. This is the sphere before it collapses, right? And it has radius r naught, right? Basically, u is only going to be valid, right? Here u is like t minus r conjugate. But if there's a sphere like chucked right there, it's going to be shifted up by plus r naught, right? So now if you have a sphere, these coordinates are modified. We're going to have a plus r conjugate naught. We can't just say plus r naught because this is like this is not in the tortoise coordinates. To keep things consistent, we have to write out the radius in terms of a tortoise radius. And then for v, well, it's going to be minus r conjugate naught because here we had a plus. So here it has to be a minus r conjugate naught. And yeah, so these are the tortoise light cone coordinates that are valid outside of the sphere. Now, r naught is the radius of the sphere before collapsing. And then r naught conjugate is just the tortoise coordinate version of the actual sphere radius. Now, since these coordinates are valid outside the sphere, what about for inside the sphere? Well, for inside the sphere, we use a different coordinate chart, right? We use different coordinates. Let's call them, I don't know, Q and S, where Q is defined as tau minus R plus R naught, and S is defined as tau plus R minus R naught. And we see that Q and S look very similar to U and V. So these are the actual interior Schwarzschild coordinates that we use to describe the inside of the sphere. So what's the metric inside the sphere? Well, outside the sphere, we talked about how we have this as the metric, where CR was just 1 minus 2m over r. Now, for inside the sphere, our metric is going to be very similar. We get this metric by solving the Einstein field equations for a non-vanishing stress energy tensor, and we would actually get A of QS dq ds. And this is the metric for inside the sphere. Now, you guys might be wondering, what is this A of QS? Well, that doesn't actually matter. It turns out that for this derivation, the actual form of A of QS does not actually matter. We can look at different models, different forms of A of QS, but at the end of the day, we don't really need to care about the actual form of A of QS. So again, we get this metric by solving the field equations for inside of a sphere, whereas this metric were solved for solving the field equations for outside the sphere. That's the vacuum solution, right? So, yeah. Now, since our sphere is actually shrinking, right, we should note that this r over here, this is going to be the radius of the sphere. Now, since the sphere is decreasing over time, or the sphere radius, this means that r is going to be a function of proper time. Now, most books write this as r equals big R of tau. I think writing it as r of tau is a bit more natural, but we'll just use this notation for now. So r is going to be a function of proper time, and at tau equals 0, right, tau equals 0, r equals r naught. So this is the radius of the sphere before the collapse begins at tau equals 0. So how do we actually derive this whole Hawking effect kind of thing? Well, we want the field to go to 0 at the center of the black hole. Why do we do that? I'm not sure, but we just kind of do. So we say that phi of u and v should be 0 when r equals 0. Now phi of uv, right, for outside the sphere, this is the field outside the sphere, it's e to the minus IKU plus e to the minus IKV. E to the, minus IKV. I wrote this as plus IKV over here should actually be a minus IKV. So minus IKV. Now we can assume that Q can be written as the function of U, and that V can be written as a function of S. And this kind of makes sense looking at the form of U and Q and V and S. So we are going to assume that they can be written in terms of each other. And yeah, so we know that at R equals 0, right, at R equals 0, we're going to have that Q equals tau plus R naught, and S is going to be tau minus R naught. So S is going to be Q minus 2 R naught for when R equals 0. So S is going to be Q minus 2 R naught for when R equals 0. So you can write V as beta of Q minus 2 R naught for when R equals 0. Now what we do here is we kind of ignore the e to minus IKU term in the field. We're only going to focus on the e to the minus IKV term in this derivation. You don't have to do that, but it's going to make things simpler to just focus on one term of the field. So just looking at that one term of our field, we're going to have that e to the minus IKV minus e to the minus IK beta of Q minus 2 R naught is going to be the general form of that right-hand term of the field. So that's going to be phi of V. This makes sense, right? Because at R equals 0, this is going to equal this over here, basically. Because V equals this only when R equals 0, right? This is not always equal to V. But when it is equal to V, then we'd have 0 for just that right-hand term. So I hope that you guys understand that we are just restricting to looking at the right-hand term of that field itself and kind of seeing what happens. So if you do that, you'd have the right-hand term will kind of become this more complicated term right over here. Now what we can do is say that at the far past, right, if you go all the way up here, right, we saw how these light rays over here kind of got like dispersed, right, in the out region. They changed their form. That's what we're kind of just describing right over here. So we can say that this part of the field, right, is going to be the in region, I guess you could say. And then this part of the field is the out region, when it leaves the actual sphere. Now, the way I see this, I kind of feel that statement is kind of dodgy, you know. Usually the entire field is this over here for that right hand side, right? I don't think it would make sense to say that one is the infield and one is the outfield from this information alone, right? But it seems like the reference that I'm using says this. I guess it kind of makes sense if you kind of think of it like the field is, I don't know. But basically, the left-hand term, e to minus IKV, that's supposed to kind of represent the field before it hits the collapsing ball. And then the complicated beta blah 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 term represents the field as it leaves the ball, kind of. Again, I don't think that's a satisfactory statement. I think there is more that should be done before making that statement, but let's just kind of like leave it as that for now. So essentially what's going on here is that by doing some more number crunching, we'll find out that this term over here is actually going to be a redshift term. In fact, beta of Q minus 2 R naught, that's actually going to be equal to something like, going from memory, C to the E to the minus IKU plus D. So we're going to have E to the minus IK times C to the E to minus IKU plus D, where the C and D, those are just constants. So this describes the field actually redshifting, right? It describes what's going on right over here. If we were to actually graph that, you'd see that the actual wave is redshifting as you approach, or as you leave the black hole, as r approaches infinity and at late times. So the main goal of the Hawking effect calculation is actually finding out this form, or proving that this form will look like this right over here. I should probably use a different like letter because the C looks like this bracket, and we are going to be solving for that form in the next video because I'm tired. So I was planning to originally make this all in one video, but like it's been a day, guys. So I'll make the part 2 of this video tomorrow. The main takeaway from this video is that the right-hand term for the field looks like this over here. And essentially, the in-field, e to the minus IKU, is converted to the out-field, e to the minus IK beta of Q minus R2 R naught, as it exits that collapsing sphere. And we're going to find out that if R is dynamical, so if like the derivative of R with respect to the proper time tau is not equal to 0, this term over here is going to be a redshift factor. And this field will actually be physically different from this field. And then we can compare these two fields with the Bogoliubov transformation. But that is a story for next time. So thanks for watching. Have a great day, and I'll see you guys then. Bye.